Okay, now let's go for the third part. We talk about the relationship of the VI for capacitor. So we will write this as the symbol, as capacitor, with capacitance C, and there is a plus and minus terminal, and the current start to go from plus to negative, from positive to negative, and this is the voltage across the capacitor. Okay, before this we have mentioned that if we assume the I equals to Im cos omega t plus theta I, right? Now, for this VI relationship for capacitor, we will use the definition of V, where for V we have V equals to Vm cos omega t plus theta V. Okay, so theta I is to define the phase for current, theta V is to define phase angle for the voltage. Okay, now we will use also the definition of I, which is equals to C dV dt. Okay, so this is now a matter on how we want to differentiate the voltage with respect to t. Alright, so I will not go into detail about how to differentiate this function. So I have now C. Okay, the dV dt is Vm negative sine omega t plus theta v, and then multiply with omega. Okay, if I want to represent this I in terms of phasor form or phasor transform, then I need to have a function of sine in terms of cosine. Okay, so what I will do is CVM, put this negative outside here, then we have negative CVM, and we have cos omega t plus theta v negative 90 degree. Okay, and also I have this omega. Okay, now if I rewrite again, okay, I need to put another bracket here. Then if I rewrite this, I will have negative omega CVM, okay, with this cosine. Alright, now if I want to do a phasor transform, so I will have this capital I with the pole, and the cosine omega t plus theta v negative or minus 90 degree here is now can be defined as, because we have this omega t, we have this Vm, and we also have this phase angle. So when I rewrite this, I will have, okay, the Vm as Vm here, and this cos, okay, is now given by the Vm and with the theta v minus 90 degree. Okay, so this is when we transform from the time domain to the frequency domain. Okay, now when I want to solve this, okay, to simplify the capital I or the current I, so what I can say is that this value is actually also the same as negative omega c with the Vm exponent j theta v minus 90 degree. Okay, so as I mentioned before, when you have two factor that you have, let's say exponent j a minus b, that is equals to exponent j a, and then multiply with exponent negative jb. Okay, so it also can be used here, and I have negative omega c Vm exponent j omega theta v multiply with exponent negative j 90 degree. Okay, and I have mentioned before that with the exponent negative j 90 degree here, okay, we have equals to negative j. So it means when we simplify this, we will have negative multiply with negative j. So you will have plus j. Okay. And we also have omega here. And we have the capacitance. And when we talk about the Vm exponent j omega v, in this case, okay, I can now write as this value of Vm exponent j omega t as the V, okay, which is the phasor transform of the V. Alright, so in this case, I can now rewrite the relationship of Vi. Okay, in this case, if I put the V, I will have V equals to I divided by J omega C. Right? Alright, so in this case, I can rewrite here also in terms of, because 1 over J equals to negative J, I can also rewrite this as negative J I divided by omega C. So in this relationship, I can write here as V equals to negative J over omega C and multiply with I. Now, if I rewrite this VI relationship for resistor as V equals to Ri, okay, what you can see here, there is actually a pattern where all these relationship of V and I, okay, for each of the component, okay, has a constant value of the impedance. Okay, I can rewrite this as V equals to ZRI, where Z is actually the impedance for resistor, and I can also write this as V equals to ZLI, where ZL is the impedance for the inductor, and I can write this as V equals to ZCI, where this Z is the impedance for the capacitor. So in this situation, I can now summarize that if I have the element and I want to define their impedance, okay, so I can write for element R, the impedance is R. Okay, for the element resistor, the impedance is R. For element inductor, okay, the impedance is ZL, which is J omega L, where for the capacitor, okay, the impedance ZC is negative J over omega C. So this is actually the summary for all impedance, okay, based on the relationship or VI relationship for each component. Alright, so I hope with this summary, we can after this apply how to use all these impedance to solve our circuit analysis when it involves the steady state analysis. Okay.